Okay, sorry, yeah. So, what we kind of talked about to end with was finding the glitches and or hazards in circuits when you have one common signal that takes a different length of path, right? So we know that anytime we use a K-map and minterms, our final circuit is going to look something like right? The sum of product expressions. Now, I could give you a different circuit, or I could ask you to design these circuits. Let's say I asked you to make a circuit that built up the state machine, right? Kind of like I talked about in the video that I posted previously. And so like, here's the state machine requirements. Now show me what the next state logic looks like. Now you're going to use a K-map for that. So let's say that it turns out like this. There's no real danger in this case of a hazard, right? Because all signals have the same path length. Now, I could change this and produce a situation in which there is potential for a hazard. And let's say that I have 3 signals that are inputs on A, B, and C. And I tell you that coming into your module, you have A, B, and C only. What that would mean is, so I'd say you have access only to the signals A, B, and C. Now let's say that I wanted A here, B here, C here, and A bar there. Right? That's possible. So the logic that my K-map puts out then would be A and B, or C and not A. Right? Well, I don't have access to not A directly, so I have to make it. Right? So I have A, I have B, I have C. Plugs in, plugs in, plugs in. But then I need to do something like right? Now I have A bar. I needed an inverter to do that. So now I have potential for a hazard or a glitch, right? Because I have one signal that has 2 different delays to the output. So the issue can be then, we can look at this and go, we know for a fact that A is the only hazard here, right? So how do we prime or sensitize this circuit so that we can test for that hazard? John, what do we do? Yeah, so the timing diagram is the second step, but I don't want to test every possible input combination, right? Because that would take a long time to do. So how do I set this up in such a way that I know that I have a chance of unveiling the hazard? That's half of it. Yeah, so the A transition, we know we're changing A. Then what do we do with B and C? They're both 1s. So that's what I refer to when I say sensitize the circuit. A is the problem, so we know that's what's going to change. If I want A to have an effect, B and C need to be sensitized. They're going into AND gates. That means 1. Going into OR gates means 0. Right? Because if I have an OR gate of A and B, and I wanted to test if A is working, and B was 1, what is the output if B is 1 and A is 0? 1. What is the output if B is 1 and A is 1? 1. So in this case, it is not sensitive to A. If B and C are both 1 here, the output of the circuit is sensitive to A, right? And we can then go on and realize essentially what could happen, right? So if B is 1 and C is 1, we're now sensitive. Then if A is 1, we would have 1 and 1. That means the output is 1, output is 1. We have a 0 here, so we have a 1 here, a 0 here, a 1 here. If A is 0, this is 0, but C is 1, A bar is 1. So this is 1. And this, still 1. Right? So what we would like to see is if I transition from 1 to 0 or 0 to 1, I always see 1 at the output. Is that going to be true here? So if A goes from 0 to 1 or 1 to 0, I want this to always be 1. I don't want to see that. Exactly. We can say with a fairly high degree of confidence, as long as these are not ideal, we're going to have a glitch, right? And that could, if we're building this back into a state machine, put us in a situation where we go into an unknown state, right? Okay. So that's kind of the brush up explanation. I will do a video that kind of goes through the timing so that you can kind of watch and rewatch, because I know this is tricky, but it is important. And this, more importantly than anything really, this will help you learn timing diagrams, which are kind of a big deal. But I want to move on to the next topic for now. What I want to do now is walk this back to the beginning of state machines. Because everything about this, we're circling around the state machine, right? And we've now had a lab that we've started building up a state machine in VHDL. And we've had some homework that talks about it. So let's say that I want to design a state machine, and these are great examples of seeing them all the time. So I want to design a circuit that detects the sequence 1, 0, 1, right? Something like that. So what it's saying is, if I get those in order, I want to detect them. I want to output a signal that says, look, I saw it, right? So that's what detect means. I had one of these questions. Detect, I say, I want to detect 1, 0, 1. What I'm saying is measure the input and assert an output when I see that, right? What is the first step? What do I want to do if I tell you to design the state machine? And let's say I tell you I want to design the state machine in VHDL. So we're not going to have to design the circuit, right? When we're doing VHDL, we don't do circuit design so often, we write code. But what is my first step? The state diagram, yes. So the first one I always do is identify whatever my state 0 is going to be. Now, a lot of times I'll call this idle or something. This isn't quite idle. This is just nothing's been detected, right? So if I get a 0, if I get a 1, I get to go to another state. And then when I have a detect problem, and it's not just detect problems, lots of these, I will design the path that works, and then come back and fill in all other paths. Okay, so I go 1, 0, 1. Now, this is a bit of a question, right? So I could say here, and then I get 1, 0, 1. Well, let's say, and this is, well, I say, I want to design a more state machine. So a Mealy state machine, I could do this, right? And I'm good. Not quite. In fact, let's stick to the Mealy state machine for a quick second. Why is this one not quite correct?
Well, so that's constantly reading though, isn't it? So
yeah, so let's finish this off for a minute, right? So that's a 1. So we go 1, 0, 1. That's not really true, is it? So if I do 1, 0, 0, that happens. Okay. So this one still is not quite correct. Say that I get the sequence 1, 0, 1, 0, 1. I see a 1, 0, 1 here and a 1, 0, 1 here, right? So what I would like to see at my output is a 1 here and a 1 there. Okay. Do I get that? No, because I do 1, 0, 1, 0, 1. Right? So this path is not correct. What I really want in order for this state machine to work okay. Yeah.
So if that were more, we would just go to Z1 and then back to S1.
Well, if this is a Moore state machine, this is a good question. This is where I'm going. So Moore, the rule of thumb with a Moore state machine is I need more states. Okay? Because the issue is I need to assert my outputs inside of the state. So right now, this depends on I'm in state 2 and my input is 1. Then I get Z1. But I can only depend on the state in a Moore state machine. So let's do the Moore. One, 0, and then 1 says, I have detected something. Right. So now I have a new state whose whole job is to assert that output. So I'm going to call this Z1M for Moore, which is confusing because Mealy and Moore are the same thing, but whatever. So let's say I have Z1M here, where I'm going to get 0, 0, 0, 1, because there's now a delay. Because in order to get this output, I have to do 1, 0, 1. Actually, maybe there's not a delay in this case. So on a clock cycle, clock in a 1, move. Oh, but it updates, right? Yeah, so I don't get to move until the next state. So then what I kind of expect is that, right?
So S3 always go to S1?
Well, that's a good question. Let's start. So what I like to do, as I said, is start with the correct path. And now we can figure out what else happens in each of these states. So S0, nothing special changes, right? S1, same kind of thing. We're still here if we saw a 1. Because this state is saying, I saw 1, 1. So I go 1, 1, 1, 1, I'm still here. So 1, 0, where does my 0 go? 1. Okay, so now I've detected. If I do 1, 0, 1, 0, right? Because this is how I think through this. I actually just follow it. So I can start back in 1, 0, 1, 0. Where do I go? Yeah, so this one is saying I saw a 1 and a 0. And then 1, 0, 1, 1 goes where? S1, because that's saying I saw a 1. So here's my two state machines, Mealy, Moore. Okay, so when I write this in VHDL, and I'll pull up a screen that, and I will actually walk through it. But let's think about what this means for the VHDL code. For the Moore state machine, the Moore state machine is essentially easier to write in a way because it's more straightforward. If I say something like, in each of these states, all I'm saying, if data in is something, state equals something else, right? And then when I finally get to here, I say Z1 equals 1. Everywhere else, Z1 is 0. And I just move through. Here, in order to get this output correct, right? Because the output depends upon both the input and the state that I'm in. So I need to write something like a combinational statement outside of the process where Z1 is equal to, well, two statements. I'm going to call this just data, saying data is equal to 1, and I'll call it current state is equal to S2. Right? Does everyone see this? Does this make sense? Okay, so that's a combinational output. Inside of the Moore state machine, I don't need to do that. I literally just have this structure, right? I have a case on CS is when, and I'll write the one for S3 at the moment. When S3 Z1M is equal to 1, if data equals 1, then CS is equal to S1, else CS is equal to S2. Right? So VHDL, again, saves us a whole bunch of work because we don't have to go design these circuits to make this decision for us. We just make it in code. And we make all of our states using the same kind of when structure. And I'll go do an example on this, okay? So here I have a combinational output because I need to react to what the input is doing independent of being in the state. And here I need to only assert inside of the state. Mealy, more. Yeah. This one should work, that one could work. Well, so you actually have a bit of an issue with that one because you're thinking of it as a mux, but you need to complicate your logic just a little bit more than you did in order to make that style work. So you could say Z1 is equal to 1 when this and this, else 0. Or you could do this. They're functionally equivalent. And something you'll discover, we don't really cover it much in this class, and I'm not even sure I'll cover in 3610 because it's kind of like outdated essentially, is you can design a whole bunch of logic using little more than muxes. Muxes are incredibly versatile. So there are situations where you would design complicated logic with nothing but muxes. We don't really do that because the focus of this really is kind of modern digital design, which means VHDL. Do you have another question over here?
Yeah, so back with the more statement, I understand like when we detect a 101, but can you explain why we go back to like S2, 0, like S1?
Yes. So let's follow this structure. If I get 1, 0, 1, it's true. We know that's true. Now I need to be in a situation where I'm ready to still detect the next 1, 0, 1. If I go back to S0 from idle, I could detect this sequence, right? But I can't detect 2 in this sequence. So what I'm doing is I'm priming it, saying that if I get 1, 0, 1, 0, I've already seen a 1, 0.
Oh, so then when you get a 1, it detects.
So then when I get the next one, I'm already back here.
So it's like detecting like, so 1, 0, 1, it detects that, but it overlaps with that last one.
Yes. Yeah. Yep. And maybe you would have a circuit that you don't want to detect overlapping, in which case you would go back to S0.
You said that needs to be outside of the process.
This is outside of the process.
Yeah.
That's combinational.
Would you say you prefer to design more machines because you do the process, or does it not?
Well,
either way?
I prefer more. You'll still have this process inside of the Mealy state machine. In fact, the only thing that changes for the Mealy is this, essentially this line, where I assert the output inside of the state. And so for the Mealy, I don't have that line. I have this outside of the process, and then I call this state 2. And now I have my Mealy case. So it's actually very similar. Not too much harder, but I think better in more.
Yeah. So you always require data to change from state to state?
In this case, yes. But what I'm doing really is I am transitioning states every clock based on data. So the process that this is inside of is clock. And I'll show the full code. I will put up code and we'll walk through it. So what it's saying is at each clock, let's decide what state we go to, right? So in the state 0 case, each clock, if it's not 1, we would just hang out here, clock 1, 1, 1, right? Now, the meanly state machine, you will actually notice, because it's outside of the process, will update outside of the clock logic. So it doesn't have to change on the rising edge of the clock, it changes on whenever data changes. Okay. I should have left that up there. Oh well. So let's keep that in our heads. And now let's talk about, there's a concept where you have, well, multiple vocabulary words, and I'll try and make sure that you're familiar with all of them. Essentially, you'll hear me refer to it as either one process or two process state machines. And you'll also hear this terms next state decoder and output decoder. So you can say things like, let's combine the state machine and the output decoder, right? Or sorry, let's combine the next state logic and the output decoder. That's essentially what a Moore machine is. So the output decoder is what is deciding what the output is. The next state logic is deciding what the next state is going to be. These two things can be separate or combined. So if they're separate, this is not how I generally design these, but it's worth showing. And this book has plenty of these types of examples. So one thing that we have is a process on clock that has something like if rising edge, right? This part is important. Then, so a process on clock, if rising edge of clock, I'm just gonna ignore that. Then, current state is equal to next state. Now that process doesn't do a lot else. Its whole thing is updating the next state logic. The other process that I would have is, I don't want to process on clock. I want to process on whatever my inputs are. So data and maybe a reset, right? So now I've got a synchronous reset. And again, what I'm going to do is here is where I'm going to have my case. And I'm going to case on current state. Sorry. When S0 if, sorry, let me think of this. I'm trying to remember the state, right? If data equals 1, then next state is equal to S1, else next state S0, right? So what is happening is this is essentially combinational logic. We're still in a process, but you can almost think of this as combinational because it's just going to update whenever data or reset changes, right? It's not clocked. It just reacts to data and reset. Now, we may have to, depending on your type of circuit, we may have to include current state. And that's probably a good thing to do in this one as well. So what's going to happen is data changes, this updates, and then this process, when the clock happens, goes, let's update current state to whatever the next state has been decided for. Right? So here I'm deciding the next state. Here I'm updating current state to next state. And then maybe outside of this process, I have the combinational statement. So here I would have and process Z1 is equal to blah, 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 right? So here I have my next state logic, sorry, my next state decoder, my output decoder, and then the state updater. I can't remember what the book calls, I think they have a different term for that. I'll have to look back and see what they call it. Right, so I have three parts. This is as partitioned as you're likely to ever make it. But I can start combining things, right? So by turning this into a more state machine, I get rid of this. And I put my output decoder inside of my next state logic. I can then combine my process, my state updater, and the decoder logic simply by saying instead of next state, I just say current state. So, your book uses what I refer to as the two process method all the time. 90% of the time I write a state machine, I combine this one and that one. So, let's see if I can't make this overhead projector work. Hopefully nobody came to school stoned. That might trip you out a little bit. Okay, let's pull up some Vivado. Can you guys see that? I didn't think so. I can make it bigger. I just have to remember how. No, it's actually kind of obnoxious because I think I have to restart the program. Ah. Make it huge. So I have to relaunch Vivado to make this work. Oh. Okay. Cool. So now I'm going to switch to Zoom and tell it to record my screen because that's probably a little bit better than. Not really. Sorry, there's the thing I'm looking for. For some reason, I can never remember where I share the screen from, and I don't know why I struggle with that so much. Okay. So here we have a skeleton structure for a single process state machine. That's where I'm going to focus on because that's how I kind of design things. It keeps it a little simple. Let's look at the parts that we have, right? So what we have is.
When you say single process, does that just mean there's one output?
That means I use one process to update the state and decode the next state.
Oh, so it's kind of combined like we were talking about.
Yeah, so I have the process on the left and the process on the right. I'm combining those two into one process here. So the entity I'm calling sequence detect, secdet, and I have input, data, clock, and reset. I have output, detect. That's saying, aha, I've seen it, right? I have created what we call the enumerated type, right? This is always part of your state machine creation, where you're going to say, my state type is, and then say what states you can have. If I need a for state, which if I'm doing a more state machine, I did, right? So I would go and say S3 is also a valid state. Now, I'm going to create, what are you unhappy about? Oh, I did an M instead of a comma. Then I create a signal that I'm calling current state, CS, that is of type state type. So its type is state, essentially, right? Now, this begin is for the architecture, process on clock and reset. Here, what type of reset is this? Asynchronous. Because it is outside of this. So this is not quite correct yet. And I left this on purpose, right? So if reset is 1, otherwise let's start doing the cases. What am I missing? Exactly. So else if rising edge of clock, then, right? Now I only react to the rising edge instead of whenever clock is 1, it would do this stuff. And that would be problematic. And you would get weird errors that would take forever to debug. So what I'm saying here is if rising edge of clock, then let's evaluate what we do. So here, when we're in S0, if data is equal to 1, we want to go to the next state. Now, in a way, that's all I need to write. I don't need to say else current, right? So I'm saying current state is that. Then when the next clock happens, what it's going to do is say the rising edge clock happens, let's case, oh, CS is S1. So it's going to evaluate the next step in that case. Now, if I were doing 2 processes, I would have to say this is next state, and I would have another process that says current state equals next state, right? And that would update. But I'm not, I'm combining them. Something that you want to look out for is I can leave this and not do else if data equals 0, then CS is S0, right? That's kind of implied. Yeah, because if I don't update current state, it stays whatever it was, right? Yeah, so here, if my current state is S0, my current state's not going to change unless this happens. However, what actually happens behind the scene, and this is different than software, is that it doesn't treat it like if data update state, otherwise don't update state. it treats it like if update state, otherwise don't care. So it's literally saying, otherwise, I don't care what state you go to. But we clearly do, right? So in order to avoid accidental optimization into breakage, add your else ifs. And in fact, it would be really good to add a solid else and then I really could combine those two, right?
Yeah.
That's kind of a repeat. And this particular one is not problematic because it is either 1 or 0. So this is currently unnecessary because there's data can't be anything besides 1 or 0 in a real circuit. In simulation, however, it can be 8 other values, right? If you remember the data types of standard logic, standard logic has 0, 1, high Z, low Z, X, U, I forget, that's most of them. I'm missing one, I think. Right? So it has all of these different things that it could be. In simulation, if I put those, who knows what's going to happen? In hardware, it's 1 or 0. High Z just means I'm not setting it to anything, but it's going to have a 1 or 0 value. So this is actually sufficient for implementing in hardware. It may, however, confuse your tests if you ever screwed up data and set it to Z. Okay, then in order to build the next state, I would do the same thing. When S1, then we do, well, again, we decide if data is equal to 0, then current state updates to S2, right? And let's push through some of these. When S2, if, ooh, S3. And I like to clean up my end ifs like you see me doing so that I don't end up with error bars. And it helps me kind of debug as I go. You can debug all of your errors at once if you like, but I'm not a fan of that. Okay, so here I've gotten through my path, right? Just kind of like how I wrote the state machine, I've now written all of the states that I need in order to detect something. Now we're at state 3. This is where detection happens. So I just write Z1M is equal to 1. Oh, right. I call it det in this, don't I? And then I can do if data is this equal. And I can go fill in those decisions, right? Boom, I'm done. Not really, right? I have to go back and fill in all of these other options. You might notice the issue with detect right now. I don't know if you see this, but this would be really beneficial to pay attention to. Right now, I would detect 1 time, and then it would stay 1 forever. I have no way of setting detect back to 0. So I would have to go back to my previous states and add, right, at least the states that I can go back to, where I would then go detect is 0 here because I know I can go back to S1 and I can also go back to S0, detect is 0. And I could also reset in the middle of state 3. If my reset happens, I go to state 0, so it turns out I actually also need detect there. Right, so detect is always 0 unless that. So that's how I make a state machine. Sorry, you had a question?
No, I'm good.
Okay.
So is that how in our lab with the garage door, is that how we would want to open, close, we want to do it inside of the state?
Again, this is one valid option. Is inside of the state, you assert those signals.
That's how I do it.
Or you can have a separate output decoder that I would do like down below. So this process has that end process. You could write the output decoder here as combinational logic. That is also perfectly fine. Either one of those works. Mealy state machines have the benefit of they react to the input quicker. So if you're in a weird situation where every clock cycle matters, Mealy state machines can be better. That's generally not the case. Most of the time, we don't care about one clock cycle. That's really what I wanted to cover. I'm going to switch the Zoom so I don't forget. So that's the main method of building a state machine. Do you guys understand if I were to give you an assignment to build a state machine that you could at least do this? Is there any remaining confusion on state machines?
Do it in BHD out.
Yeah.
I feel like I could puzzle it out.
I mean, that's fine, but
For the most part.
okay. So what we're gonna do now, while I still have time, is I'm going to talk about project 3. The last thing that we have to do as far as labs go in this class. So, project 3, if you remember project 2, which I'm sure you've all put it far out of your memory and forgotten everything about it, but you're provided with that test bench, right? And it asserts all of those signals for you. What we want to do is create control logic that does what that test bench did based on a single command. So, if you pull up project 3, which I believe I've posted, you would see that it gives you something like, let's declare a constant. You know what? Let's do a different one. Okay. So here's an example of what it does. I want to declare a constant called operation add I, or add immediate. When I do that, it's going to be operation add I is going to be an 8-bit standard logic vector that holds the value 0, 0. Or it could be 0A, because this X quotation is telling us that this is an 8-bit hex code, right? So now, if anywhere I were to write op add I get this. So now I need some sort of control logic that, based on a clock, is going to pass this op add I to the rest of the project that you've built with all of its correct control signals. So I say add I. So add I means add immediate. So one of the things that we could have, the difference is just add. And that might be da 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 da. That's a different command. Add wants to pull data from a memory and add it. Add immediate, I pass a value with this command. The next thing I pass it is an immediate value, and it adds it in. It adds that value. So what we're doing is thinking about what each of these commands are supposed to do. And you can see, you actually have really good examples for most of these commands in the test bench, right? So you get this command, and it tells you this command should be add immediate, and then it asserts, the test bench does, all of those signals for you. What you're going to do is you're going to write the logic that says, well, when I get this command, let's make those control signals instead. This lab does have for you a method of creating a memory. So you don't have to worry about creating the memory at all. It's just there. You just need the controller that we kind of built, right? And then it also shows you how to model that memory. So we'll make the memory, model the memory, and that's really it. There's not too much complexity to this. It's just kind of like keeping, it's just, what's the word I'm looking for? Accounting. It's just accounting for all of your little variables and making sure that all the signals come out correctly. I apparently was a little sloppy and I didn't post the grading thing, but this is basically, you get the point if the thing works, right? This code will have to be synthesizable. So one of the things that you'll need to provide for me is a synthesis report that I explain in the lab handout. You can still get partial credit if it doesn't synthesize, but for full points, it needs to synthesize. Do you have any questions? I mean, I know you might not just because you don't know yet, you haven't dug into it, but at the moment, do you have questions?
Where's the state machine coming?
Well, this one may or may not need a state machine, depending how you execute it. But so the last lab, the garage door opener was like the bulk of our state machine lab stuff. There was supposed to be one more. I just kind of cut it for time. But this one, we can kind of think through how do you want to execute all of these signals. So one of the ways that you could do this, and probably how I do this, is I need to assert a whole bunch of signals, right? The read, the load memory, the mar, all of that stuff, based on this command. So let's start in idle. And now we need to do something, right? We need to execute a command. So the hard way of doing this is you would have one arrow out for every single command. That's probably not the best way of doing it, but it's kind of a brute force. It'll work and might keep things clear for you. But I'll just call this command, where it's going to have an output of opcode, for example. So it's going to translate whatever the command that it got into its opcode, which your ALU needs. It also needs like read, load mar, right? So these are going to be all of your outputs. Now, this is not quite the right way of writing it because these are all kind of variables. But how I would do it is I would assert all of those signals based on it. Now, there's one more step to that is because of the fact that I may not want the next command immediately. Because I may need to, the first part of this might just be setting things up. Like in the case of add immediate, right? And I'll have to go back and double check that that's what they did here. But you can kind of tell inside of the test bench that you were provided. Some of these steps take multiple clock cycles to execute, right? Usually kind of 2. And so maybe you want to have command 1, command 2, command 3. And these will always step through maybe, right? And you would say, okay, the first thing that I have to do when I want to add immediate is prepare all of the signals that say to add. And then the next thing that I have to do is send it whatever it is that I'm adding. And then after that, I can go back and and maybe we don't call this idle, we call that next command, right? This is going to take some thinking about how you want to implement it. And we may need to deal with 3 stages if we're, I don't know, adding something and then saving it to memory. But this is how you would start thinking about the state machine, is just looking at what it takes to execute each of these commands. And then maybe having branches if you need them to help yourself.
So there are some commands that depend on other commands, but then having been called before it.
Sort of. So some of these commands, when you execute them, don't increment the process counter, right?
Right.
When you have those ones, you don't want to go. So here, let's not call that idle. Let's call this like PC plus, where that says get the next command. And it's going to count through process controller kind of thing and assert that signal that says increment process controller. And then it's going to take that process controller and take the next command.
Okay.
If it doesn't want to increment the next process controller, we'll have another step to do whatever else that is supposed to do and insert those signals. And then at whatever point we need to go back to the process controller, we can. So my advice is pick one of the commands, build a simple state machine that does it, and then start adding on and building up the rest of the commands that you need.
So, for example, like the add command, that needs something to get loaded, have been loaded into the accumulator beforehand, right?
Oh, yes.
Yeah, so.
Yeah, in your case.
Like, so the test bench, is it the same as last time? I haven't read it yet, but did he give us stuff to put into the test bench that's in the correct order? Or do we need to account for it?
What it's going to do is it's going to provide you a memory that has a series of commands in it.
There we go. Okay, that's it.
Yep. And we're going to walk through this, all of these operations, and make sure that you end up with results.
So yeah, he gave us the list of commands. We don't need to worry about that.
Correct. Yeah. Yeah. And so if you look at the memory, it starts by loading immediate, then it adds immediate, and then it has I have to go back and look at the last lab in order to decode what some of these are. But it'll walk you through all of those. And at the same time, what's going to happen is you're going to write these back to memory. So these have memory locations that are written. And then it's going to, you're going to store in other locations in that memory, essentially. So the memory size is 256 by 7, or by 8 rather, and it fills in like 20 commands. Everything else can be used to store data. Yep, and then it kind of gives you hints about what the process counter should be in one of the columns as well. Yeah. Let me check my notes real quick. Okay, yes, something else. I'll send out an announcement. So that's project 3. We'll start that today, I suppose. Did you guys finish the last lab by chance?
I haven't done the test bench.
Yeah, I'm trying to figure out the test.
Okay, so we can kind of wrap that up. After Thanksgiving, they have asked us to not come in if possible, which I think is possible for us. That being said, I will still be in the lab, so I will not hold class. I will still be there for lab. Because I think lab is valuable enough to be justified, as long as they let me. I have to get approval, I believe, but I'll send out an announcement with all the details for next Monday. But classes will be just video posts, essentially. I think I'm going to do them asynchronously. So rather than like having a Zoom kind of just talking to a brick wall, I'll post a video and then during class time, I'll be on Zoom to have discussions if you have kind of leftover questions. The good news is I kind of accelerated the timeline and we've covered 98% of what we need to already. Which is, I mean, we're almost done with the class, right? Day of class is like December 4th or something anyways, I think. So we're really in a good shape for this semester. You guys have learned almost everything you need. You're doing pretty well. I'm happy with the exams. We'll have a final. The final will be much like I did exam 2, where you can take it from anywhere. If you take it from anywhere, you just need to be comfortable downloading like a Word doc or PDF. I usually upload both formats just in case. Adding stuff to it and then re-uploading it. We won't do an in-person final. It will be, everyone will be kind of taking this remotely. One of the things to be aware of with that, if you haven't done it, you may need to draw some things. So make sure that you're comfortable in making drawings, essentially, right? So if I ask you to draw a timing diagram of some simple circuit, you would need to be able to create in your submission, right? I would likely provide you with like this, hopefully the signals that you need, like I'll call it signal 1, signal 2, signal 3, and then just some axes. And then you would have to be able to go in and be like high, low, and oh, this one is not that with a delay or something, right? You would need to be able to create this in your Word document. Now, this could be use like a drawing tool in Paint, make an image, and then paste it into a Word document. That's fine. You can also use like PowerPoint, or if you have like a touch screen, you can just doodle on it. There are lots of ways to make it work. Just be aware that it's something you will be expected to be able to do.
Can we print it off and do it?
Yeah, if you want to print it off, do it and then scan it. Just make sure you can turn that into a PDF.
Right.
That is totally fine. So whatever your method is, as long as you get the answers uploaded, I will be a happy person. Questions on that? Okay, and I will have a review video and session before we take the final. That'll be like our last day of class kind of thing. And I'll keep in touch with you guys on how this project 3 goes to make sure it's not getting too overwhelming. And I will hopefully not have to. hopefully not too complicated. It's a fair amount of work. I think I'll have like one, maybe two more assignments to assign for the rest of the year, or sorry, the rest of the semester, year, same thing at this point. So hopefully you guys don't get overwhelmed. I don't want that to happen. Yeah.
So the homework portion is due or whenever we do. I feel like I didn't understand it well enough, but now I feel like after going through this, I feel like I understand it
You understand better? Okay.
a lot better when I did it. I watched your video and stuff, but I still didn't understand it. I don't know if I.
Sure. Yeah. I'm, again, not marking late until, well, the end of the semester, really, as long as you get it in before the end of the semester. The exception is homeworks I've posted the answers to, right? Those get marked late. Everything else you can submit. If any of you have not submitted anything, even if I posted the answers before, at least post it so you get partial credit. I would hate for anybody to do poorly or worst case like fail just because they didn't submit something. So make sure you've turned everything in. Go look at your grades and make sure it's at least submitted. I'm a little behind on grades, but not too bad. Yeah.
So I think after today in the lab, are we starting from the 3?
Yes. If you want to kind of wrap up and work, if you have like questions on the garage door opener lab, we're still okay there. We can still ask. But it would be good to at least start project 3 today so that you have an idea, so that you can ask questions to get started over the rest of the week, right? And spend some time, not on Thanksgiving, but maybe like the Friday after, since we don't have class, just kind of working through it. But at least have an idea of where you're going with it. Yeah.
Final test, will that be like everything, or will
It will be cumulative. And I will post a review guide kind of thing for that. Reviewing your other 2 exams will be really good for preparing for the final. Because what I will do, almost guaranteed, is I will look back and see what people did really bad at and put those as questions on the final. So make sure you can do the other exams. Okay, we'll call that. That's what, 3 minutes early? That's nothing. So